Dear students, good evening. M.Lingeshwaran. I serve in the capacity of an assistant professor at the Department of Electronics and Communication Engineering, St. Joseph's College of Engineering, OMR, Chennai. So I welcome you all for my lecture on antenna theory. So today we'll see the fundamental idea behind antennas, how does an antenna radiate, and what are the fundamental antenna parameters. Okay, so let's get started. So how can we define an antenna, right? So what is the fundamental idea behind an antenna? Okay, so as per IEEE standards, antenna can be defined as a means for radiating or receiving radio waves. Okay, this is as per IEEE standard. Right? Okay. So during transmission, what does an antenna do? Right? We are going to apply alternating current to the piece of metal. Right? So upon transmission, okay, your antenna converts a guided wave into a free space wave upon transmission. Right? During reception, this free space wave is once again converted back into guided wave. Okay. So that is why antenna can be called as a transition device, or we can even call it as a region of transition between guided wave and free space wave. So now let me consider a generator. Let it be a generator, right? And this is the transmission line that is feeding your antenna. So this is your TX antenna, right? So this is my generator. This is the transmission line. And this is the transmitting antenna. Right? This is basically a generator. Okay. Similarly, this is with respect to TX part, transmitter part. What about RX? You will have a similar setup, right? So you will have a line, transmission line feeding your receiver, right? So this is basically your receiver, and you have a transmission line feeding your receiver. This transmission line in turn takes power from the receiving antenna, right? This is basically an antenna. Write it here. So this is basically an antenna, right? So during transmission, this is what you will see. So here you have a guided wave. So on transmission line, you very well know you have a guided wave. This guided wave is now converted into free space wave. So this is what you will get to see in real time. Okay. So these waves will expand, right? With respect to distance, these waves will expand and they will take the shape of uniform plane wavefront, right? So they will take the shape of uniform plane wavefront. So this plane wave will strike your receiving antenna, right? So this results in excitation of your receiving antenna, right? So during the illumination of your receiving antenna, once again the guided wave gets converted into the free space wave gets converted into guided wave. So here this is your guided wave. This guided wave is getting converted into free space wave. With respect to distance, this free space wave will expand, right? This wave will expand and will become a plane wave, right? So this is basically a free space wave. Then this free space wave will get converted into a guided wave. eventually this will become a guided wave. That is how power is being delivered to the receiver, right? So this is the whole idea behind antennas. You can call antenna as a region of transition between guided wave and free space wave, right? Okay. So this is where you have your guided wave and here you have your free space wave. This region of transition can be called as an antenna, or you can even call it as, this can even be represented as, antenna can be called as a transducer, right? So here you have your guided wave. This guided wave is now becoming a free space wave. Same thing applies here. Right? So here you have your guided wave. Okay. So this is the fundamental idea behind antennas, and now let me move on to basic radiation equation. Right. So what is the idea behind basic radiation equation? So see here, let me consider a current carrying conductor whose length is basically L, right? And let the area of cross section be simply A. Okay. So now from grade 12 you will be able to recollect the amount of current flowing through this conductor will be I is equal to N into E into P into A, where N is the number of electrons, E is the charge of the electron, P is the velocity of your drift velocity of your electrons, A is the area of cross section of the conductor, right? Okay. For the sake of brevity, let me assume area of cross section as 1 meter square. Now the equation for current becomes I is equal to N into V, N into E into V, right? So this is drift velocity. So what is product of N into E? Number of electrons into charge of the electron. So let me represent this as Q into V. Okay. So we have considered length L, right? So now what will be the time varying current flowing through length L? L into dI by dt will be, right? So we have considered a current carrying conductor of length L. So this becomes L into Q into, right? So this is independent of time, but velocity definitely it is a time dependent variable. So this equation can further be rewritten as into L, into L. This can be considered as simply Q into V cap or V dot. Okay, what is the interpretation here? If you want to create radiation, right? If you want to create radiation, you ultimately need, okay? So to create radiation, you ultimately need time varying current, right? So to create radiation, time varying current should be applied to the antennas. You ultimately need time varying current. This basically indicates the charges are undergoing acceleration or deceleration of charges. right? So we need time varying current or basically acceleration or deceleration of charges. So one thing is clear now. If say the charge is moving with steady velocity, right? So there won't be any acceleration or deceleration of charges, no radiation will be created. Okay? Only if you apply alternating current to a piece of metal, that will result in radiation, provided the length matches with the wavelength. Okay? So I guess this is clear now. Now let us proceed to antenna field zones. Okay? Prior to that, maybe we can spend some more time on how radiations come out of a piece of metal. Let me consider an oscillating dipole, right? So we have studied oscillating dipole way back in electromagnetics, right? So now let us consider a dipole. What is a dipole? Dipole is basically two equal and opposite charges separated by a finite distance, right? So now we are considering fields from an oscillating dipole. Okay. So we are going to apply alternating current to the dipole element. Okay. So let me draw the excitation signal here. This is T. Okay, x of T. Right. So instead of considering the entire cycle, right, let me focus only on a half cycle, right, 0 to T by 2. So mid of this point will be T by 4, this point will be T by 8, this will be 3T by 8. Okay. Right. So now let me consider two charges, right, which are at maximum separation. Okay, since the charges are maximum separation initially, right, so they will undergo maximum acceleration. But what about current? Current is 0. Okay, that is what we are supposed to know, right? So the charges are at maximum separation. Okay, so fields of lines will start from positive charge and terminate at negative charge. Okay, it's quite very well known. So the charges are at maximum separation. Okay, so now let me come. This is with respect to time t equal to 0. Okay, so now let me consider a time period t is equal to t by 8. Okay, so at t by 8, the charges would have moved from the extremities. So they are somewhere here, right? Okay, they are somewhere here. Right? The field lines will slightly spread out, okay, with respect to time t is equal to t by 8. So now let me consider this maxima at time t is equal to t by 4. Okay. So at this point the charges would have crossed the midpoint of your dipole, right? So now this is basically your dipole. So they have actually crossed their locations, right? So negative charge move to the upper half and the positive charge move to the lower half. Ultimately, this will result in formation of loops. Okay. So see here. Right? So what will happen with respect to time 3t by 8? So now if I consider time 3t by 8, so for example, let me consider 3t by 8. So see here the thing is the the charges have crossed the midpoint. Okay, right? So now they will move in such a way they are actually getting close to the extremity. So at this point, the previous field line would have cut loose from the antenna. Okay? So see here. This field line would have cut loose from the antenna and new field lines are being formed. Right? Next, at time t is equal to t by 2, what happens? Same setup, the charges now will be at the extremities. So negative charge will be at one extremity, positive charge will be at another extremity. Right? So already the field lines are cut loose from the antenna. Right? So here, apart from this, the field lines are cut loose from the antenna, right? Okay, this would have traveled a distance of lambda by 2. So that is the interpretation you need to draw, right? Okay, so here once again now charges are at maximum separation, so current will be 0, and here current will be maximum where the acceleration is almost 0. Clear? So this is maximum. So this is the way in which electric field lines will cut loose from an antenna. Okay, and they will travel outward, right? So this will give you better insights about how electric field lines are actually originating from an antenna, right? So now let me proceed to the fundamental antenna parameters. We'll start with antenna field zones. Right. So antenna field zones. So let me consider a basic antenna. Let this be an antenna, right? And L is the length of the antenna. Right? So L is length of the antenna. Okay. So we are actually trying to draw a sphere around the antenna, right? With a radius R. So let me draw a sphere around this antenna. Right? So let the radius of the sphere L square by lambda, where L is the length of the antenna, right? So I have drawn a sphere segregating two regions around the antenna, right? So this region inside this sphere, hypothetical sphere, I call it as near field region, and the outer one I call it as far field region. Okay, near field region is also known as Fresnel zone, and far field region can be termed as Fraunhofer zone. Okay, Fresnel and Fraunhofer, right? So why is it necessary to divide the space around the antenna, right? So if you consider the near field region, right, your pattern, right, your field pattern, okay, here your field pattern, it will depend on distance. Okay, field pattern will depend on distance. Right, within this region, field pattern shape will depend on distance. But if you consider this particular region in Fraunhofer zone or far field region, your field pattern will be independent of distance. So that is why whenever we deploy a receiving antenna, the receiving antenna should be always placed at the far field region or Fraunhofer zone, just to ensure that the field pattern is independent of distance, right? Okay. Now, if you take a half-wave dipole, right? If you take a half-wave dipole, right? These endpoints, right? These endpoints, I call them as poles. Okay, here they will behave like a reflector. And the equatorial zone, this particular zone, right? This plane, equatorial plane. This is the place through which power flow will happen, right? So if this is where you will see power flow. But at the poles, right, you don't see any power flow. This is in the equatorial plane. You will see the major power flow, right? And if you try to plot this radiation pattern, right? So it will be in the figure of 8. Okay, there will be no radiation at the end points of your half-wave dipole. Okay, there is an interpretation from antenna field zones. We are dividing the space around the antenna into two zones, Fresnel and Fraunhofer, to make sure your receiving antenna is situated in the far field region of the antenna, right? Okay. So let us move on to radiation pattern. Right. Radiation pattern. So how can I define radiation pattern, right? So if you want to know what is the behavior of an antenna, right? So you can represent behavior of an antenna mathematically or graphically, right? So radiation properties of an antenna can be depicted in the mathematical or graphical form. So this is basically the radiation properties of an antenna represented in mathematical or graphical form, right? As a function of spatial coordinates, nothing but theta comma phi. Okay. So how does an antenna radiate in the elevational plane theta and azimuth plane phi? Okay, that can be either with the help of a mathematical equation or expression or graphical form, right? So what are the ways in which I can represent, right? The radiation pattern can be a field pattern, right? Or it can be a power pattern. So power pattern, field pattern, normally this is expressed in linear scale. Power pattern can be expressed in either linear scale or decimal scale. These are two choices available for us. And now, let me draw a radiation pattern with respect to field pattern. Right? So this is the direction of maxima. Right? So if I want to locate half power points with respect to field pattern, this is field pattern on a linear scale. So here I have to consider 2 points on either side of pattern maxima which are 0.707 times of your maximum. If it is a normalized one, you can say simply the maximum value is unity, right? You have to locate the points on either side which is equal to 0.707, right? Nothing but 1 by root 2. Okay, these are half power points, right? And the angle enclosed between these two, we can call them as half power beam width. Okay, so this angle is HPBW. So this is with respect to field pattern. Similarly, how can we define for power pattern? So here field pattern is in linear scale. So what is the field pattern? Here basically this could be E of theta, right, comma phi. Okay. What about power pattern? The power pattern can once again be of same shape. But what is the difference here? Instead of choosing 0.707 for power pattern, right? So this is in linear scale, right? So P of theta comma phi. In order to locate half power points, I'll simply use point 0.5. So this will be 0.5, this will be 0.5, provided this is a normalized value, this is unity here, this is unity here. Okay. Once you go towards dB scale, power pattern, normalized power pattern on a dB scale. So once you move towards power pattern with respect to dB scale, it will be the reference value now becomes, this is the power pattern. So the reference value will now become, this will be 0 dB. So 3 dB lesser than this will be minus 3 dB. Right? Okay, we have to look at 3 dB lesser than the maximum value. These are the half power points, and the angle enclosed between these 2 points, you can simply call them as half power beam width. Once again, here this can be called as half power beam width, HPBW. Right? Angle enclosed between the directions in which your antenna is radiating half of the maximum power. That is half power beam width. Okay? So along with this, right? So we can label the radiation lobes. Right? So what are the radiation lobes that are available here? So if you look at the radiation lobes, okay, so this is my major lobe. I can call it as major or main lobe. Right? And rest of the things I can call it as side lobes. Okay? And the largest side lobe, I call it as minor lobe. And this one, this radiation lobe, which is exactly opposite to the maxima, I call it as back lobe. Okay? So radiation pattern can even be represented in the rectangular form instead of this polar form. Okay? So if you try to represent this in a rectangular form, right? So you'll have your maxima, this is theta. You'll have your maxima in some side lobes, right, with respect to theta. Okay, so now this is your maxima, right? So this is your side lobe. And how can I define another parameter called first null beam width? So these are the points where you have your null. Okay, right? So these are the points where you have your null. This is is nothing but the first null beamwidth. So angular separation between the directions in which your antenna is not radiating any power at all. So there are two beamwidths I have mentioned, right? So one is half power beamwidth, other one first null beamwidth. Okay, right? So half power beamwidth, the angle between the directions in which your antenna is radiating half of the maximum power. First null beamwidth, it is the angular separation between the points where your antenna is radiating zero power, where nulls are available in the radiation pattern. Okay, so with this I am going to wind up the first session. Okay, nothing but the introduction to antennas and fundamental antenna parameters. Okay, so in the next session I will discuss few more antenna parameters which are highly relevant with respect to antenna design. So I would like to thank every one of you for your time and patience. So let me wind up the session here. Thank you all, and if you have any doubts, the material will be posted, okay, in all the public forum. So you can post your questions in the forum. I will try to answer to those questions. So thank you all.